I'm Mouzhan Moinian and I'm going to talk about problem number 6, the irreversible Cartesian diver. The problem statement says a simple Cartesian diver, for example an inverted test tube partially filled with water, is placed in a long vertical tube filled with water. Increasing the pressure in the tube forces the Cartesian diver to sink. When it reaches a certain depth, it never returns to the surface, even if the pressure is changed back to its initial value. Investigate this phenomenon and how it depends on relevant parameters. This is our initial observation. When we squeeze the bottle, the diver sinks, and after crossing a certain depth, it spontaneously sinks and doesn't come back to the surface when we decrease or release the pressure. This is our roadmap. Here we have a simple Cartesian diver. This is our diver. When we squeeze the bottle and increase the pressure in the bottle, the diver sinks, and when the pressure is decreased, the diver returns to the surface. What happens to a simple Cartesian diver? The behavior of a Cartesian diver is unique and doesn't occur with normal buoys, but why? When we squeeze the bottle, the air inside of the diver is compressed and water enters the diver. As a result, part of the initial volume of the air that is inside of the diver gets replaced by water. As the density of water is much bigger than the density of air, the density of our diver rapidly increases and it causes our diver to sink. When we release the pressure, water comes out of the diver. So the volume of the air increases and reaches its initial value. Thus, the density of our diver returns to its initial value and our diver returns to its first position that was floating on the surface of water. The density of our diver changes due to the external pressure, so by increasing the pressure, the diver sinks. Now let's take a closer look at what happens in a Cartesian diver. When we squeeze a bottle, we increase the total pressure in the bottle, and then our diver sinks. Now let's take a look at our diver. This is the initial length of air column in the diver, and this is the initial length of water column in the diver. Air is compressible, but water is not. So by the rise of the total pressure, the air inside of the diver compresses, and its volume decreases. So it allows more water to come inside of the diver, so the volume of water inside of the diver increases. As a result, the density of our diver increases, and then our diver sinks. An irreversible Cartesian diver is a simple Cartesian diver that remains at the bottom of the bottle, even when the pressure is released. These are our assumptions. The air bubble in the diver feels only the ambient pressure plus the pressure exerted on the surface of water. Temperature is constant and does not change during the experiments. Water is practically incompressible, so its density is constant and does not change with depth. And the trapped air inside of the diver behaves like an ideal gas. At first glance, we have the forces that are acting on our diver. The buoyant force that is being applied to our diver, the diver's weight, and the dissipative force proportional to velocity. When we can have an irreversible Cartesian diver? From both of our theories, we can realize that in a bottle of an irreversible Cartesian diver, there is a certain depth called the critical depth. When the diver crosses that depth, it spontaneously sinks and doesn't come back to the surface when we release the pressure. But in a simple Cartesian diver, usually the bottle isn't long enough, so the diver always remains above that depth. So when it reaches the bottom of the bottle, the buoyant force will return to the surface when we release the pressure. So what is the condition for never returning again? If we don't consider the drag force, we can realize that beyond the critical depth of our diver, the buoyant force that is being applied to our diver is lower than the diver's weight. So the weight of our diver will hold our diver down, and the buoyant force won't be enough to overcome it and return the diver to the surface when we decrease the pressure. So we wrote this equation of motion, but as this term must be disparted, but we left it like that, and also we haven't considered the drag force, we decided to improve our theory. Now we're going to investigate the behavior of the diver in different pressures. Suppose we have this test tube in P0 pressure. The length of the air column inside of it is L0 and the length of the test tube is L. And suppose we have this bottle, but the pressure of the air inside of it is P. We place our test tube inside of the bottle. The new length of air column inside of it is L. That is obviously smaller than L0. Here we have X, that is the distance between the end of the diver and the free water level, and alpha, that is part of the air column in the diver that is submerged. We suppose our diver is the test tube's glass plus the trapped air inside of it. When we increase the pressure, X becomes lower, until at a point it equals 0. At that point, our pressure is a critical pressure, which is defined as a pressure in which the end of the diver is at the same level as the water surface. And when we increase the pressure past the critical pressure, our diver spontaneously and completely sinks. Now let's discuss the first static equilibrium of our diver, when the pressure of the air inside of the bottle is P, and we call alpha E because our diver is in its static equilibrium. The mass of the trapped air inside of the diver is negligible compared to the mass of the test tube. So according to Archimedes' principle, we can write this equation. This term is the buoyant force exerted on air that is submerged, and this term is the buoyant force exerted on glass that is submerged. Now we will write the equilibrium equation when P equals P star. Here we have alpha star E that is equal to L. So we can write this equation. This quantity depends only on geometrical parameters and on the two densities. We suppose Xc is much smaller than L, so we can neglect that and realize that alpha E is approximately equal to alpha star E, and we suppose the transfer inside of the diver behaves like an ideal gas and temperature is constant and does not change. So now, according to Pascal's principle and Boyle's law, we can rewrite what we wrote in the previous step like this, and if we simplify that, we will reach this equation that gives us Xt. P is equal to P star, so Xt is equal to 0, so we can simplify even further and reach this equation. As we know, this term is much smaller than P, so we can neglect that and reach this equation. Finally, after putting so much effort, it gives us something useful, and from this equation we can realize that these four parameters are related. When x is bigger than 0, this equation is holds for it, and if it's smaller than 0, this equation. Now let's take a look at the dynamics of our diver. In order to derive the equation of motion, we have to use Newton's second law. There are four forces acting on our diver: the buoyant force on air, the buoyant force on glass, the diver's weight, and the dissipative force. So now we have this differential equation that we want to solve to reach xt. Here we have b, that is the constant coefficient of the velocity, and we calculate from its formula. Cd here for a cylinder is 0.82. Xt is approximately equal to 0, so alpha t is smaller than alpha star e, so we can write this equation, and if this equation is held, the net force that is acting on the diver might become negative and it causes our diver to sink. Our diver sinks when it reaches the no return depth. At that depth, x is equal to x and r, and alpha is equal to alpha star e, so we can write this equation to calculate x and r, and if we simplify that, we will reach this equation that we are going to investigate in our experiments. We used Python for our simulation, and we gave it these initial conditions that we measure. We have an ordinary differential equation, so we used this library in Python and gave it these initial conditions. X is equal to 0, and we obtained v0 using tracker. This is our experimental setup. We use a cylindrical tube as a bottle with 1 meter height and 10 centimeters diameter, a removable lid at the top of our cylinder, a test tube as the diver that we marked it with black tape so that we are able to track it with tracker, a pump to apply pressure on the liquid surface, a three-way stopcock to control the air admittance, a one-way stopcock to control and maintain the pressure, a medical digital money image, and a ruler. So now with this setup, we are mechanically applying pressure on the water surface, and we are able to measure that. And also these are the test tubes that we used in our experiments. In this experiment, we are displacing the diver from its first static equilibrium a little. And as you can see, we can observe some damped oscillations in our diver around its equilibrium point. Here we have the irreversible Cartesian diver. When we increase the pressure, our diver sinks, and when we release the pressure, our diver remains at the bottom of the cylinder. In this experiment, we are investigating the different motions of a Cartesian diver with different L0s. So we use four identical test tubes with different L0s. Here we have diver A, diver B, diver C, and diver D. Diver D immediately sinks when we put it in the cylinder without any increasing in the pressure. And when we increase the pressure, diver C sinks. And by increasing the pressure further, diver B sinks too, because its critical pressure is more than the critical pressure of diver C and less than the critical pressure of diver A. But diver A remains on top because its critical pressure is too much that we are not able to apply that. And when we release the pressure, diver B returns to the surface, but the position of other divers don't change. In this experiment, we use one diver that we are varying its initial velocities. This is the graph when the initial velocity of our diver is v1, when it's v2, and when it's v3. And if we compare the graphs that we had from our experiment with the graph that we had obtained from our theory, we can observe a good agreement. And if we do this comparison with V3, we can also observe a good agreement. In this experiment, we use one diver that we are varying its L0s and measuring the critical pressure for each L0. And as you can see, these parameters have a linear direct correlation. If we compare our theory with our experiments, for alpha star E, we can observe a good agreement. For alpha star E plus x and r, we can also observe a good agreement. And for holding of this equation, we can see that this equation is being held. We wanted to make a Cartesian diver that doesn't come back to the surface when the pressure is released and to find the relevant parameters. Our theory said these following parameters are important, and by adjusting them we can have a Cartesian diver that when it goes below a certain depth it never returns to the surface. But the irreversible Cartesian diver also can be achieved by some other ways, for example by using two liquids in the bottle with different densities, using absorbent material in the diver, etc. When the external pressure is changed and the diver goes below a certain depth, at the same time we can have an irreversible Cartesian diver. That critical depth depends on the pressure and the initial amount of water in the diver. When we give a small perturbation to a diver at its equilibrium point, it has some damped oscillations around its equilibrium point. By adjusting identical divers but with different initial conditions, for example L0, initial velocity, etc., we can observe different motions. The diver completely sinks when it reaches the no-return depth, and when the pressure is dropped to the critical pressure, it spontaneously sinks. And we observed good agreements between our theory and experiments. These are our references. Thank you for your attention.